All of you, good morning. Now we will discuss about fundamental fundamentals of digital image processing. So here the prerequisites for this subject image processing are signals and systems. We had to know what is signal, what is signal. After that, digital signal processing. So anyhow, in this title, digital image processing, we are having three words: digital image processing. First of all, we will discuss about digital. So we know that we are having analog signals, discrete signals, digital signals. So in brief, so analog means so any signal consists of coordinates, that is x-axis and y-axis. So here generally the variable which is taking an x-axis will be independent variable. Now in analog signal, both coordinates, that is both if you take f of t is independent variable, t as well as f both are continuous, time and amplitude both are continuous. Whereas in digital signal, time and amplitude both are discretized, both are discretized, and they are having non-zero finite values, non-zero finite values. This is digital. Now come to image. Image is nothing but two-dimensional system. Two-dimensional system. Now come to processing. Now, what is processing? What is the need of processing? So in general, the acquired signal or image is not suitable for my work or application or my project. Then we have to process the image so that I can get better image than the acquired image. That means we have to process the image. We have to send the image to some algorithm. We have to apply some algorithm on this image so that I can get better image. Or we have to process the image to some computer. So finally the output image will be much better than the input image. Input image or original image. So this is digital image processing. Digital image processing. Now we will discuss about digital image processing fundamentals. In this, first, what is an image? An image is nothing but two-dimensional system. Whenever we are telling two-dimensional signal, immediately what is one-dimensional signal? As we know that one-dimensional signal mathematically can be represented as small f of x or small f of t or small x of t. So here x or t is independent variable generally taken on the x-axis. Now on the y-axis we are taking f of x, f of x. So here f is amplitude, f is amplitude. So here the signal f of x is one dimensional signal. So here if only one independent variable, that is here x is independent variable. So here in the bracket we are having only one independent variable. So then the f of x is said to be one-dimensional signal or simply 1D signal. Now, if you take f of xy, f of x comma y, so here in the bracket we are having two independent variables, x and y, x and y. So then here f is amplitude. Generally, f of xy is called two-dimensional signal or 2D signal or image. So here x comma y are spatial coordinates and f is amplitude. That means it represents some gray level or some color value, So anyhow, f of xy is nothing but two-dimensional signal, or we are calling the two-dimensional signal as an image. So therefore, here image is nothing but two-dimensional signal, but we cannot call all the signals as image because one dimensional signal cannot be called as signal. Image must have two independent variables. Independent variables. So this is signal and image. So finally, we can say that image is nothing but two-dimensional signal. Two-dimensional signal. Now, so images are two types: analog image and digital image. So here, image can be represented as small f of x comma y, where x and y are spatial coordinates, and the amplitude f is called intensity or the level value or color value at, at the point x comma y or at the coordinates x and y. So here, so in the analog image, both coordinates, that is x comma y, and as well as f are continuous. F are all are continuous values. X, Y, F all are continuous. So then that type of signal, that type of image is known as analog image. Analog image. Now digital image. So here, so digital image here also it is digital image is represented by f of x, where x, y are spatial coordinates. So f is intensity, gray level or color at the. So here x comma y and f all are finite and discrete quantities. All are finite and discrete quantities, not continuous. So here discrete quantity. This is a digital image. Digital image. Now, if you see one example, a simple example, how can you represent any an analog image as well as digital image? So here I am taking a letter T, where the T totally consists of black color. Totally consists of black color. So here wherever is the black, then we digitize this letter T. Now wherever black color is there, those are represented by zero value. Zero value. Wherever white is there, we can represent by using one. By using one. So now this is, so here continuous. This T is continuous, that is analog image, whereas so 0, 0, 5 zeros in the first row. The middle column consists of 0, remaining columns are constant. So this is the representation of digital image for the analog image, capital T. Capital. So this is simple representation of both analog and digital images. Digital images. Now we can, here we can conclude that a digital image is composed of finite number of elements. Finite number of elements, each of which has a particular location. Now, at particular location, we are having some finite value. Finite value. That means these elements, that means in an image we are having elements at particular coordinates. We are having the finite values at particular coordinates. So here those elements are referred as image elements or picture elements. So these picture elements are abbreviated as well. So in picture we are taking the first letter P, and in second word elements PEL is taken, and combinedly PEL are abbreviated as cells, or most commonly we are calling these picture elements as pixels. Hmm? Pixels. So each picture is represented by some finite numerical value. Finite numerical value. So in general, the pixel value is related to brightness or color at the particular location. So finally, you can say that image composed of pictures. Image composed of pictures. Now we can represent image in matrix form. Representation of image, digital image in matrix form. So we know that the image consists of so many elements. So each element can be represented one element in a matrix. So first element at the left topmost corner, the element is represented as small f of 0, comma 0. That means spatial coordinates are 0, comma 0, and amplitude, that is intensity value, at 0, 0 is 0. Similarly, second element in the first row can be represented as f of 0, comma 1. Next f of 0, comma 2, so on, f of 0, comma n minus 1, n minus 1. So similarly, in second row, f of 1, comma 0, f of 1, comma 1, so on, f of 1, comma n minus 1. So on, if write there are m rows, we can write last row f of capital M minus 1, comma 0, second element f of capital M minus 1, 1, so on. At the last we are having f of capital M minus 1, comma capital N minus 1. That means here we are having total 0 to M minus 1 rows and 0 to N minus 1 column. That is total M rows and N columns. M rows and N columns. So here each element in this matrix is known as image element or picture element or picture. So each element, that is f of 0, comma 0 is one picture, f of 1, 0, comma 1 is one picture, like that. So finally, f of xy can be represented in the matrix form as shown. Matrix form as so. This is the representation of digital image in matrix form. Matrix form. Now, how many types of images are there? We are having black and red image, black and white image or binary image, second gray image, gray level image, third one color image, color image. Now one by one we will discuss. First, black and how can you represent black image? So here I am taking one image at the left top. I am taking an image. So black and red image. So in that a small part is taken. Finally, a middle part, a small middle part can be shown like this. So here half of the part consists of black color and half of the part is white color. Therefore, in general, in image processing, black color can be represented by zeros and white color points are represented by ones. Therefore, so in binary we can represent 0, 0, 0, 0, 0, 0, 0, 0, and third row 1, 1, 1, 1, fourth row 1, 1, 1, 1. So this is the black and white image and it represents. Anyhow, in this black and white, wherever we can take, whether it may be black picture or white picture, only two colors will appear in this black and white image. So black and white image is also called binary image. Binary image. So in general, 0 represents black color, white represents white color. So this is about black and white image or binary image. Now, gray level image. Before going to gray level image, so how can you represent image? 1-bit image, 2-bit image, or 3-bit image. 3-bit image. Generally, each pixel can be represented. So in an image, each pixel can be represented 1 bit, 2 bits, or 3 bits. Now, if small n is taken as number of bits, so then we will get 2 power n gray levels. 2 power small n gray levels. If small n is number of bits, so then 2 power small n, 2 power small n gives us number of gray levels. Number of gray levels. For example, if n is equal to 1, n is equal to 1, we will get 2 power 1 is equal to 2 gray levels. Though the two gray levels are 0 and 1. 0 and 1. 0 represents black, white represents white. If n is equal to 2, we will get 2 power 2, 4 gray levels. 4 gray levels. So these 4 gray levels are represented in binary format 0, 0, 0, 1, 1, 0, 1, 1. Or we can also convert these 4 gray levels, these 4 gray levels, so which are in binary form, also can be converted into decimal form. So 0, 0 decimal equivalent 0, 0, 1 decimal equivalent 1, 1, 0 decimal equivalent 2, 1, 1, 3. So like that. So instead of 0, 0, 0, 1, 1, 0, 1, 1, we can also write 0, comma 1, comma 2, comma 3. That is 4 gray levels, that is 0 to 3. So including 0, 0, 1, 2, 3. There are 4 gray levels. There are 4 gray levels. So now, how can you represent 1-bit image? Suppose if you take 3 by 3 image, so here 3 rows, 3 columns. 3 by 3 means 3 rows, 3 columns. So 3 into 3, we will get 9 pixels. 9 pixels. So here each pixel is represented by 1 bit. 1 bit means each pixel is represented by 1 bit. So here is one example 0, 0, 1, 1, 1, 0, 1, 0, 1. So this is the representation of 1 bit 3 by 3 image. 1 bit 3 by 3 image. Similarly, if you take example 2, 2 bit 3 by 3 image. So 3 by 3 means 3 into 3 we will get 9 pixels. So here each pixel is represented by 2 bit number. 2 bit number. 2 bit binary number. So here is one example 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, 0, 0. So here at 2 power 2 we will get 4 gray levels. 4 gray levels. That means the gray levels must be in between 0, 0 to 1, 1. No other value. So this is 4 gray level, grow levels image. Similarly, 3 bit 3 by 3 image. So 3 by 3 will get 9 pixels. Each pixel is represented by 3 bit number, 3 bit binary number. So here one example is given 0, 1, 0. So how many gray levels exist? 2 power 3 will get 2 power 3, 9, 8 gray levels. So we'll get 8 gray levels. What are the 8 gray levels? How can you represent in mathematics the binary form? 0, 0, 0, first gray level, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So total 0 0 0 to 1 1 1. So if you convert 0 0 0 in decimal, you will get 0. 0 0 1 in decimal 1. 0 1 0 decimal 2. So like that 0 0 0 that is 0. Last number 1 1 1 that is equivalent decimal number is 1. That means we will get 0 1 2 3 4 5 6 7. Total 8 numbers. In 3-bit number, we will get 8 gray levels, that is 0, comma 1, comma 2, comma 3, that is up to 7. 0, 1, 2, 3, 4, 5, 6, 7. Depending upon the picture, so we will get the values. We will get the value. So this is the brief discussion about how can you write 1 bit 3 by 3 image, 2 bit 3 by 3 image, 3 bit 3 by 3 image. And similarly, in the same fashion, we can write 4 bit number, 4 bit image, 5 bit image, 6 bit, whatever it is. There are 2 power 8, so then we will get 256 gray levels, 0 to 255. Total 256 gray levels. Now, see how grayscale image can be represented. So, here one example is taken, a small part of the image, a sub image. So, finally, here in third template that can be represented in gray level values 10 10, 16 28 9 6, 26 37, 15 25 13 22, 32 15 87 13, like that. So here, so which bit, what is the bit size here? So you can see 87. That means so if 2 power 5. hmm, So here maximum number is 87. So therefore it may be 2 power 7, maybe 7-bit number. There is no chance of 6-bit number. 6-bit means 64. We'll get 64 gray level. So here we are having maximum number is 87. So obviously it may be 7-bit image, 7-bit, 7-bit image or 8-bit image, 8-bit image. So this is gray level. First of all, what is gray level? Suppose if we take 0 and 1, 0 and 1. Suppose for our understanding purpose, I am taking 1 liter paint box one side, so another side black color paint box. So this is pure white, this is pure pure black. Pure black is represented 0, pure white is represented by 1. Suppose if you take black color point in 4 spoons, 4 spoons, now pour 1 spoon of black color into white paint. White paint. What will happen? So here instead of white, pure white, we will get some shade in between black and white. Black. That is one gray level. If you pour another spoon, we will get another shade of the color in between 0, 1, 0 and 1. That is another gray level. Similarly, third spoon, we will get another gray level. So fourth, we will get another. So that means, so here whenever black color added to the white, automatically we will get various shades. Each shade is known as one gray color. Each shade is one. So similar, we can take, if we can make black color into 8 parts, 16 parts, 32 parts, 64 parts, 64. So depending upon the number of spoons, so when you add each spoon, you will get different gray color, different gray color. So this is about gray. Now, how can I represent color image? How can I represent color? So here some tree image. So in between a small sub image is taken. Finally, in third template. So in each, so suppose there are 4 by 4, 4 rows, 4 columns. There are 16 pixels. 16 pixels. So in color image, each pixel is represented by RGB. Red, green, blue color. A combination of RGB values. Generally, RGB, red, blue, green. These three colors are known as primary colors. Primary colors. Why they are called primary? Nothing but our eye can easily see thousands of colors, thousands of, but RGB will easily grasp. That is, in our eye we are having the cones, cones are uh, easily seen the RGB color. So in RGB, red will be highest, uh, red will so easily, therefore R is the first color, G opposite G. So these three colors RGB are known as primary color. Primary color. By mixing RGB values in different places, we will get secondary color. So we will get secondary color. So here our point is, so each pixel. So in black and white image, each pixel is having either it may be black or white. Black or white. In gray color, each pixel is represented with some gray level value. Gray level value. So now here in color image, each pixel is represented by R as well as G, the combination of RGB. Therefore, each pixel is having three values R, G, B, R, G. Therefore, we can this total subimage can be represented by three templates R, G, and D. R, G, and D. So in gray level means we are having only one template. Here we will get three templates. One is for R, one is for G, one is for D. One is for. So therefore, in comparison with the gray level, the color image takes more number of bits. The color image can be represented by more number of bits comparatively gray 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 level images, gray level image. So this is about what is anime, what is image processing. So how many types of images are there? So now we will close the session. Uh, in the next slide, in the next lecture, so we will be somewhat deep in this next part. Thank you for watching. Nice to see you. Thank you and all.